Hello everyone. Today let's solve the problem number 105. Construct binary tree from the preorder and inorder traversal. So this is what the question states. So you can just go through the question and you can just go through the examples as well to understand the question pretty well. So I'll just summarize the question so that it will be easier to understand. So we are given two integer arrays here. So we are given two integer arrays. One is preorder and one is inorder. So what does preorder indicates here? Preorder represents the preorder traversal of a binary tree. So preorder just represents the preorder traversal of a binary tree, and inorder represents the inorder traversal of the binary tree. So in the previous problem, we have solved the problem using the iterative inorder itself, right? So by this time you will be knowing the inorder. Let's discuss the preorder further, right? So just understand, preorder represents the preorder traversal of a binary tree, and inorder represents the inorder traversal of the same tree. So what we need to do here, we need to construct the original binary tree using these two traversals and return the root nodes. So that's what they have mentioned. This is important, right? Just keep in mind, we need to reconstruct the original binary tree by making use of these two traversals and return the root node. So that's what they have given here. So we are just returning the root node here. We are reconstructing the tree by making use of the preorder and inorder traversal, and we are constructing this one new tree and we are returning the root node. So a root node has to be the this one. Root has to be the output finally, right? So that's what they have given here in this case. So first, for this example, you can clearly see they have given 3, 9, 20, 15, 7 and 9, 3, 15, 27. This is in order. This is pre-order. They have mentioned the output here is 3, 9, 20 null because no value exists for this one, the node with the value 9, right? So we are considering for the left subtree null and for the right subtree null, and finally 15, 7 for the node, this one, node value 20, this one, right? So same goes with the second example as well. Preorder -1 they have given, inorder -1 they have given, output -1 because we have only one element, right? So the output will be obviously -1 here with the value, right? With the value -1 for the node. So let's discuss the approach first, followed by edge cases one by one, and then finally write the code and the complexities of the code that we have written. Initially, as usual, we'll be discussing the approach. So here let's discuss the approach step by step. First thing we have to keep in mind here is we are making use of divide and conquer with the recursion or recursive approach, right? So to reconstruct the binary tree. So we'll be making use of, just remember this one, divide and conquer with recursion. So we are going with the divide and conquer with recursion. Just remember this one. So first thing, we need to understand that what is preorder and inorder, right? So we have already discussed the inorder. Let's discuss preorder first. So preorder, order will be in this case root followed by left subtree and followed by right subtree. This is preorder. And what is inorder? The previous problem we have seen the same thing actually. It starts from left, then root, then followed by right. This is the order that we need to consider for the preorder and inorder. I hope this is clear. In simple terms, if I want to say, the first element in preorder is always the root of the current subtree. The first element in the preorder is always the root of the current subtree, this one, 3 in this case. So using this root value, we find its position in order to separate left and right subtrees. So that's what we will be doing. This will be the first step. You just we don't have to stress too much about this one, what I've said later. Just we should be knowing this one, preorder and the inorder. The second step is steps to rebuild the tree. So we have to rebuild the tree, right? By making use of the in-order and the post-order traversal, we have to reconstruct the tree or rebuild the tree. Let's move with the rebuilding the tree. Nothing but here. Let's consider this one step by step. This is nothing but steps to rebuild tree, right? So here in this case, we will be making use of preorder of 0 for the root. We will be making use of preorder of 0 for the root, right? This is the first step. So after using the preorder of 0 as the root, the next step is we have to find the index of this root in order, right? So that's what we discussed in the previous step. We have to find the index of this root in the in order. Then what we will do here, we have to find index of this one of this root in order. Then we will recursively build the left and right subtrees. Here comes the recursion mainly. We will recursively build left and right subtrees, right? Left and right subtrees here. So left subtree, when I say left subtree, what I'm speaking of, values before the root index, right? Left subtrees, we are considering in order here. Left subtree is nothing but the values before the root in the in order. Values before root index or root. Just consider values before root index. So for the right subtree, values after root index. Root index. This is fine. Values before the root index and values after the root index. This is for the left subtree and right subtree. So why we are considering this one? Because we are recursively building the left and right subtree, right? So this is the step. So we have seen the first step, second step, and the third step, right? So this is fine. This is for the third step. Then let's move on with the fourth step. After recursively building the left and right subtrees, we have to keep an index. So this is important. We have to keep an index. Why we are doing this one? We have to keep an index to track the next root in preorder. Just to track next root in preorder. This is fine. The final step is we are making use of the hash map as well. So why we are making use of the hash map? How the hash map will be useful here? Because we have to store the in-order indices, right? For big of one lookup, we'll be making use of the hash map to store. Mainly, we have to store the in-order indices. This we know. To store the in-order indices, we are making use of the hash map. Let's forget about the lookup part. Just we are making use of the hash map to store in-order indices. So these are the steps. This is the approach that we'll be going with. First thing, we are going with the divide and conquer method, right? So divide and conquer with recursion to reconstruct the binary tree. First step, what we saw here, we saw what's in-order traversal and the pre-order traversal, the order of the node that we saw. And next step is steps to rebuild the tree. That's what we have to do. That's what the question is about. And first step was we are making use of preorder of 0 here as the root. Next step is we have to find the index of this root in the in order. Second step. Third step, we are recursively building the left and right subtree. This is easy, and this is the important step as well. Left subtree, values before the root index. Right subtree, values after the root index, because we are considering here this is for the in order traversal. So left subtree, values before the root index, and right subtree, nothing but the values after the root index. And the fourth step is we have to keep an index. Why we are keeping an index here? To track the next root in the pre-order. And finally, final step is we are making use of the hash map. Why we are making use of the hash map here? To store the in-order indices, right? So that is the reason we'll be making use of the hash map. So this is the approach that we'll be going with. So next, what we'll do, let's discuss the edge cases one by one. So the first edge case that I'll be going with here is this one, single node tree. When I say single node tree, input, let's consider here preorder. For the preorder, I'll just consider P. For the inorder, I'll just consider I. For the preorder, I'll just consider -1, as we are going with a single node. For inorder also, I'll just consider -1. The output will be -1 in this case. Why? Because root here is for the preorder is -1. Inorder -1. Inorder also -1, because we are having only one node here. So the output will be quite obviously -1. Here we are not having any left or right children at all, right? So the output will be -1 in this case. This is for the condition single node tree. This is fine. Let's move on with the second edge case here. Now, second edge case is nothing but here left skewed tree here. Let me give here first itself. I'll give left skewed tree. When I say left skewed tree, I'll consider here example preorder 5, 4, 3, 2 and 1. For the inorder, I'll just consider 1, 2, 3, 4, 5. This is fine. This is for the left skewed tree. So first we are picking the root from preorder 5. Here you can clearly see. First we have to pick from the this one, preorder 5. We have to find the 5 in the inorder. Here we have to find the 5 in the inorder. It is at the root index 4, right? So 0, 1, 2, 3, 4. It is 5 is at the root index 4. 5 is at the index 4. Now the left subtree should be 1, 2, 3, 4. In this case, there is no right subtree at all, right? In this case. So how can we write this one? This will be 5, 4, 3, 2, 1. This is nothing but the 5, 4, 3, 2, 1. This is correct, right? Yeah. This is for the condition left skewed tree. Only left subtree we are considering here. Only left children exists. This is similar to the linked list. We can clearly see here, right? This is similar to the linked list. Right subtree is empty. Here you can clearly see this is empty. Right subtree here. This one is empty in this case, right? So this is for the edge case 2. Let's move on with the third edge case, nothing but right skewed tree. Previously we saw left skewed tree. Now we will see right skewed tree. Hope this is clear. So here only right subtree has to exist, right? So I'll just consider preorder 1, 2, 3, 4, 5, and inorder let me consider here 1, 2, 3, 4, 5 itself in this case. So first we have to pick the root from preorder 1, this one, right? And we have to find the 1 in inorder here itself. It is at the index 0, right? So this is at the index 0. So no left subtree here. No left subtree here. Right subtree will be 2, 3, 4 and 5. This will be the right subtree in this case. So we can just write in this way, right? 1, 2, 3, 4, 5. So only right children exist here. Left children is here. This one left subtree. This is empty in this case. Only right children exist here, right? So the left subtree is empty in this case. This is for the condition right skewed tree. Let's move on with the fourth or the final edge case. Fourth edge case, let's consider balanced binary tree here. So let me give here balanced binary tree. So balanced binary tree, when I say balanced binary tree, I'll just consider the preorder 3, 9, 20, 15, 7 here. And inorder, let me consider here 9, 3, 15, 27. This is fine. This is inorder, this is preorder. So we have to pick the root from preorder, this one, first element, right? 3. This one we'll be considering. We'll be looking at the value 3 in the inorder. Nothing but it is present at the index 1, right? So we can clearly see here. This is found at the index 1 here. So root is at the index 1. We know this one. So left subtree will be 9 here in this case. Left subtree will be 9 in this case, and the right subtree will be, this will be the left subtree, and the right subtree will be, right subtree will be here, this one. Other elements, that is at the right side, 1527 in this case, right? This will be the right subtree. So how can we draw the tree here? First, this will be 3, starting from this one, starting from 3, 9 and 20, finally 15 and 7, right? So the output will be this one itself, right? Whatever I have drawn the diagram, that will be the output here. So we have discussed 4 edge cases. One is for the single node tree. Second one was for the, just give me a second here. Second one was for the left skewed tree. Third one was for the right skewed tree. And the fourth one, or the final one, was for the balanced binary tree. I hope all the edge cases are clear. So next, let's start writing the code. So let's write the code. Initially, as we had discussed in the approach, we have to keep track of the root position in the preorder. Also, we are making use of the hash map to store the index of each value in the in order, right? So let's let me consider index here, and let me initialize this one to 0, and let me consider here hash map here, just to store the index of the each value in the in order. This is fine. Next step is we have to store the in order indices in the map, right? So we are just storing all the in order indices in the hash map, right? For the quick lookup. Just remember this one. We are just storing the in order indices in the map. I can write in this way, right? In order. So let me make use of the for each here. For this one, I'll just give consider value as well as the index. So here map of value within the array. This one, let me initialize this one to the index. This is fine. So next step, after storing the in order indices in the map, what we will do, we have to recursively build the left and right subtrees, right? So let's make use of the recursive function to build the tree. So I'll just give here, let me consider the function name as build here. Let's pass the parameters, left and right subtree. We have to this one consider, right? Recursively left and right. So I'll just pass the parameters left and right here. This is fine. Within this, the base case, we discussed already this one, right? The base case was if no elements is present in the subtree. So how can I write this one? If left greater than right, then we can just return null in this case. So the next step is we have to pick the root node from the preorder first. That's what we have done. We have discussed each edge case one by one, if you remember. We were picking the root node from the preorder initially. I showed every example step by step, right? So first we have to pick the root node from the preorder. So I'll just give here let node equals new tree node of this will be preorder of index. Let's increment this one index. We are just picking the root node from the preorder. After picking the root node from the preorder, we have to recursively construct the left and right right subtrees. So we are making use of the recursive approach, right? So we are recursively just constructing the left and right subtrees. I'll just give here node dot left. This is equal to build recursive function. We are just making use of the function name here. Left and map of value of the node, this one minus 1. So we are considering the left subtree here, nothing but the before root index. So after root index also we have to consider nothing but the right subtree. We are considering left subtree, nothing but before root index. Now we are considering the right subtree after root index. So I'll just copy the same thing and make the necessary changes over here so that I don't have to type this one again. So I'll just give here dot right here build here. This one comes first in this case of node dot in this case, instead of -1, +1, because the right one we are considering, and instead of the left, we'll be considering right. I hope this is clear. So next step is we have to return the constructed subtree. So we just give a return node in this case. Final step is, so just give me a second here. Final step is we have to start from the full range, right? So here we have just in this function we have just we are just returning the constructed subtree. In this case, last step, we have to start from the full range. For that, let's return here build start from the 0, and we will consider the last index nothing but inorder dot length -1. This is fine. I hope this clear. Let me format the code once. Let me hit the run button. So I can what preorder is not a function. Where I have considered this one? Line number 10. Node equals just. So here what I have done, this one has to be within the array. Preorder of index. We are incrementing the index here, right? This one has to be within the array. Let me run this one again. So you can clearly see now the sample test cases are getting passed, right? So let me hit the submit button now. So you can clearly see all the test cases are getting passed here. So the code works absolutely correct. So let's quickly discuss the time complexity and the space complexity of the code that we have written. So the approach that we went with here is divide and conquer and recursion, that we know. And what will be the time complexity, or the overall time complexity here would be big of n. Why time complexity here is big of n? Because we are processing each node once, and lookup in order, right, which is of index big of 1. We are making use of hash map for that, right? So index lookup takes big of 1, and we are processing each node once, which will take big of n. So the overall time complexity would be here big of n. So what will be the space complexity then? We are making use of the hash map. In worst case, we have to store all the elements, right? That will be of big of n. And also we are making use of the recursion stack. So the overall space complexity here for the recursion stack also, if we consider the space complexity, would be big of n. So overall space complexity would be here big of n as well. So the space complexity and the time complexity and the space complexity would be big of n for the code that we have written. So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.